The focus of today's talk is going to pick up in many ways right where we left off, focusing on addition of nucleophiles to metal pi bond containing systems. We focused the previous talk on Walker type nucleophalidation. We're going to wrap up that discussion with a brief overview of the other key mode of addition to alkenes, Heck type carbo-palladation, and then we'll spend the majority of today's lecture focused on allylic substitution, which you'll see a lot of the same themes come up again. I think these two topics go together quite nicely in many ways. So let me go ahead and share my iPad. And let me know, blink in Morse code if this isn't sharing. Okay, it looks like it's working to me. Is everyone able to see this? So this bit of notes really will serve as sort of a primer to, or a natural introduction to, again, what we'll talk about for most of today, which are allylic substitution reactions. So in addition to these processes whereby nucleophiles can add to CC double bond systems, there are namely alkenes. There are related processes where nucleophiles can add to alkynes, as well as conjugated alkenes, namely 1,3-dienes and 1,2-dienes or allenes. And so let's look just briefly at what intermediates are thusly generated, and then you can think about what the reactivity consequences of this will be. So in the case of an alkyne, nucleophilic addition generates an alkenyl palladium, and depending on the nature of the nucleophile and the coordination sphere around the metal, two potential regio chemical outcomes are possible, as well as two potential stereochemical outcomes. So I'll just draw the two potential stereochemical outcomes. And this is at least to my knowledge, not readily predictable based on first principles. So certainly in the case of an aryl palladium migratory insertion, those are always syn stereospecific, but things like acetate as nucleophile, they can participate either in a syn or anti fashion, which muddies the water a little bit. Maybe I'll just push arrows here just to kind of illustrate this in crystal clear terms. So analogously, addition to a 1,3-diene, and I've drawn a cyclic flavor here, and result in a pi-al species. Here two potential stereochemical outcomes. Here's the syn outcome. Here's the anti outcome. And then allenes, though they're a little bit disguised in some way, they end up reacting similarly to 1,3-dienes, and so the nucleophile can either attack at the internal position or at the terminal position. And I would say maybe the internal position might be the more common of the two. Sorry, this doesn't really look like an arrow. in the case of the, now you have sort of a hybrid of the two reactivity modes. In the case where the nucleophile engages the terminal position, you would get this alkenol palladium. And then, as I said, what's the more common of the two, you would get this allyl palladium. So again, I think part of the power of these pi bond addition processes are not that they're limited to any particular nucleophile or any particular pi system, but that there's a lot of generality across different coupling partners and substrates, and that's the root of their use for assembling molecular complexity. Okay, let's talk now about Heck type carbo-palladation. As I said, we'll go through this quickly because we already covered this in the context of 1,2 migratory insertion, and now we'll just put the finishing touches to see how this integrates in catalysis. So first, let's walk through the mechanism of this and what gets spit out at the end. So starting from this aryl palladium 2 alkene intermediate, what is going to happen here? Jun Chen.
Sorry, Kiri, what's your question?
Just what's going to happen from this intermediate starred here?
So you will have like migratory insertion.
Okay. Let's draw the just 4-membered transition state there, so everyone's crystal clear on that. So Jun Chen is saying 1,2 migratory insertion. Okay, that is going to give us a alkyl palladium, where these two groups are now installed syn to one another. And this is an important point, and this is really what I wanted to comment on. So let's draw the implicit H atoms here as well, just for complete clarity. So what's next, Jin Chen?
Then let's rotate the CC bond and make the hydrogen atom at the same phase, and then do the beta hydride animation.
Perfect. So the key point here that I just wanted to draw everyone's attention to is this need for a rotation that Jun Chen so insightfully pointed out. That ends up, it's required to position these in a syn oops, sorry about that. Syn relationship to one another, which is a prerequisite, at least for classical beta hydride elimination. There are some more exotic mechanisms where you can avoid this, but unless you see otherwise, you know to expect otherwise, then you should know that these need to be syn, and this complicates the situation, particularly when you get to cyclic systems, as we'll see. And then beta hydride elimination. And again, another key point I just want to draw your attention to is that then the overall outcome is that if you look at the geometry of R1 and R2, these get inverted as a fundamental part of the reaction, fundamental aspect of the reaction mechanism. Super, okay. Any questions on that? Let's go then into some early history where this reactivity paradigm was first fleshed out. And in the early days, 60s, early 70s, the reports were pretty scattershot, to be frank. And so it took a while to put this all together into a really comprehensive framework. So one of the first examples of Heck-type carbo-palladation, what we now refer to as Heck-type carbo-palladation, comes from the lab of Fujiwara, where they take this palladium-2 styrene complex, which I've drawn here in quotes, meaning that it's not the real structure. So maybe I'll ask for a volunteer if anyone wants to provide a structure. The hint being that palladium-2 styrene, if you just drew this out, this would be 3-coordinate and I guess 14 electron palladium, which would not be stable. So how would you expect this palladium-2 styrene to exist? Any volunteers?
Do you have the dimer?
Okay, what kind of dimer? What's bridging?
Bridging chloride.
Beautiful. Okay, thank you. I think that was Carter. Okay, so we have this palladium-2 styrene dimer that's basically refluxed in the presence of an arene solvent such as toluene or benzene and acetic acid, and what's spit out at the end is a stilbene complex. And so if you look at the oxidation states involved here, it's palladium-2 going in, and as we'll see later in the CH activation lecture, palladium-2 plus arene plus a carboxylate base is normally a recipe for what's called a concerted metallation deprotonation type CH activation. And that's how you generate the key aryl palladium intermediate. That then engages the alkene in this process that we defined above in terms of that mechanism. Fujiwara, I think, is not, my own opinion, is not credited enough for this, for many things, but for this, the connection here to the foundations of organopalladium chemistry, but it is what it is. Okay, now let's fast forward a year and look at an example from the Heck lab. I think back when he was working at Hercules chemical company, he spent his career affiliated between there and the University of Delaware. Actually was a colleague of our crystallography collaborator and treasured UCSD colleague, Arnie Reingold. So here's an example. Now we take diphenyl mercury, and if you think back to the timing here, this is in the late 1960s. So the Wacker type process is now online. People are trying to explore that chemistry. You saw this early report from Suji where they use 1,3-dicarbonyl nucleophiles, and people are asking what other nucleophiles could engage here. So that's the origin of Fujiwara's exploration. And Heck here is asking, could we potentially coax an organometallic reagent to participate in a Wacker type process? And so that's the experiment that he ran. And indeed, this is a good way to make stilbenes or beta aryl acrylate type products. And here too, we go through a palladium-2 aryl, now formed via transmetallation of the aryl fragment from mercury to palladium. And one important note here is that this is now catalytic, and if you look at these conditions where we're using copper as a co-catalyst, you'll appreciate the connection to the early Wacker chemistry. And so as this mode of reactivity has become further developed, this has been referred to as an oxidative Heck reaction. There's some irony here because actually the first report is this now called oxidative Heck. But how can you have something that's oxidative if the reaction itself wasn't defined before? And I guess you'll see that shortly. So the first report was oxidative Heck, and then the more familiar sort of redox neutral Heck process, which I tend to refer to as the Mizoroki-Heck reaction for reasons that will become obvious shortly. So these two papers were in the literature, and then in short succession in the early 70s, reports from Mizoroki and Heck defined this or established the viability of this alternative redox couple. So here you'll appreciate that we're going with palladium-2 and some nucleophilic organic moiety, whether that's an arene CH bond or an organometallic. Now we have the opposite polarity where we're coming in with an electrophilic organic fragment and palladium-0 as the catalyst. So you see that in both cases, we actually use palladium-2 as the pre-catalyst, but this is reduced in situ. And this is corroborated by observations like the fact that palladium black also works in the Mizoroki case. And now the key difference is that the same type of aryl palladium species is generated, but it's generated by oxidative addition. And the importance of this observation, of course, is that now this sets the conceptual underpinnings for this revolution of cross-coupling, which typically are palladium-0 mediated processes that proceed via oxidative addition, transmetallation, and reductive elimination. So that's the connection to this new thread of research that we'll pick up in a few lectures' time. And there's some tragedy here in that Mizoroki passed away at quite a young age, so never got to really enjoy the fruits of his labor or see how his discovery really pervaded the whole field of organometallic chemistry, unfortunately. Okay, let's walk through this now, just putting together these pieces. I'll ask for one volunteer just to really unpack this for us. Daniel, can you just walk us through these elementary steps now in the classical polarity Mizoroki-Heck reaction? Palladium-0 encounters an aryl halide, and then what happens here?
Yeah, so the first step would be oxidative addition.
Okay, let's draw that. And I'll draw this with a high level of detail, just so we can really see all of these steps, some of which are hidden that you don't necessarily appreciate. So oxidative addition is going to orient those two groups that have added now in a syn fashion. And so this, I'll just tell you, is an equilibrium and pretty fast equilibrium, typically, not always, but typically with the trans form. Oops. And now we have alkene coordination. What ligand is the alkene going to coordinate here, Daniel? Or displace?
Okay, yeah. The X.
Okay, you have two options here, X or L.
Oh, so then is it L?
And it's this one. I stacked the deck in your favor because you can answer either, and you can be correct depending on whether you're in a neutral or cationic pathway. So let's draw the neutral pathway, which is I guess the more common of the two, where we've lost L. This is coming in, which means I guess I should draw this L coming out. Okay, now we have 1,2 migratory insertion. As we saw, we have this bond rotation step that Jun Chen nicely spelled out for us. Oops. Beta hydride elimination, and then as we saw previously, there is this discrete process where the metal hydride needs to get off the alkene, find base, and that indeed is a key thermodynamic driving force in this reaction. Let's see, did I miss anything in my notes? I think I got it all. So we mentioned this.
Sorry, I have a question about this
Sure,
mechanism. So I don't know whether it is obvious, but what is the reductance to reduce gradient 2 to gradient 0 in the beginning of the mechanism?
Yeah, we'll talk about this in more detail in the cross-coupling lecture. There are a couple different possibilities here, depending on the reaction conditions. I'll just draw one possibility here. So let's say that you have triphenylphosphine as your ligand in excess. And actually what can happen is the phosphine is a sacrificial reductant. And out comes this is not the only way you can do this, but just one way. Phosphine oxide.
Okay, thank you.
Yeah.
Sorry, Kiri. I was just going to ask the same question, and I don't want to belabor it too much. But so in these sort of seminal reports here, what there's not a phosphine there, or so where does the palladium 0? So like you drew the palladium 0 in pink up there.
Yep.
But then so how does that work in that case? I mean,
great question, Brendan. So let's say in this case where we have a ethylamine, then what can be generated is something like this. So the amine is the sacrificial reductant in that case. And then likewise, you could draw an analogous process where methanol could serve as the sacrificial reductant in the Mizoroki case. So we'll review these now we basically covered this. So we'll review it and when we get to cross coupling, but it's a great observation. And it's a tricky part, to be perfectly frank, I think when I was new to this field, it's a tricky thing to get your mind around because you can't just look at the oxidation state of the pre-catalyst and know what catalytic paradigm you're in. You have to think about what's the oxidation state of the pre-catalyst, what ligands are present, how reducing are those ligands, what other additives are present, what are the coupling partners. These all, I think, need to be taken into consideration. Okay, I'll just comment very, very briefly on this point that Daniel nicely alluded to, if I can manage to get my notes up. I always have this problem when I'm using Zoom that the window that I want is buried beneath like a million other windows. So hopefully you will have received a day 13 handout, which just maps out some of these catalytic processes. Some of these mechanisms you will already have in your notes, but this allows you to compare Walker oxidation, classical Mizoroki-Heck, oxidative Heck, these different processes, and also makes a point about how to think about whether you're in a neutral or cationic pathway. So some of the signaling elements are for the neutral pathway are when you're using let's say aryl bromides, aryl iodides, and monodentate phosphine ligands. In contrast, the cationic pathway signaling elements, alarm bell should be going off in your mind if you have, say, like an aryl triflate where the counter anion that is thusly generated is going to be weakly coordinating. You might expect that to be easier to push out, and indeed that's the case, as well as bidentate phosphine ligands. And this does have important reactivity and selectivity consequences. And so again, this is in the handout, so I won't belabor this point, but the site of addition to various alkenes does depend on which pathway you're in or which mechanism is operative. So in the case of really activated alkenes like acrylates, the reaction is 100% beta selective, typically in either case. But when you get to non-conjugated alkenes, now the story is a little bit different. You have like an 80-20 split for being in the neutral pathway versus a 60-40 split for the cationic pathway. And for alkenes that are polarized, you can think of in the opposite direction. Here you have a 60-40 split in the neutral pathway, and actually essentially perfect selectivity for the internal position of the cationic pathway. And I'll leave it to you to think about the origins of this in terms of the nature of that migratory insertion step, which typically is going to be selectivity determinant. Okay, we'll wrap up the Heck discussion here. Let me switch over to other notes. So now we'll focus on a nucleophilic attack onto a different type of organometallic, namely these pi-allyls. We alluded to this when we covered the Green-Davies-Mingos rules, and now we'll see these. We'll revisit these in a more systematic way. And I think just in terms of how the electrons move in this, the key difference compared to what you saw previously is in a metal-allyl complex, typically the terminal positions are where the partial positive charge accumulates, and then upon nucleophilic attack, if you push electrons, the metal actually gets reduced, such that the product that is formed, or the intermediate, if you're talking about a catalytic cycle, is a metal alkene complex that is now in the N-2 oxidation state. And so this is sort of like a hybrid between a nucleophilic attack and a reductive elimination. I think we typically will just refer to it as nucleophilic attack of a pi-allyl, but you need to keep in the back of your mind that it's reductive at the metal center. And so metal allyls are a little bit special in being compared to other X-type organic fragments that we have encountered before. So if we make this comparison of metal-allyl, and another one that's related here are metal-acyls, because they're actually electrophilic at the carbon that's directly attached to the metal, and that stands in stark contrast to alkyl metals, aryl metals, or alkenyl metals. And that's because these others that are highlighted in blue, they lack a low-lying LUMO for any nucleophile to engage. And if you just think about how the charge density, these are, you'd say are all delta minus. There are examples of nucleophilic pi-allyls, but I would say those are more the exception than the rule. Typically, and certainly in terms of what we'll cover in today's lecture is mostly electrophilic metal-allyl species. And then in terms of their reactivity trends, as a first approximation, because these are reacting as electrophiles, you would expect cationic to be more reactive than neutral, then in turn to be more reactive than anionic. And these anionic metal-allyls is when you start to see the nucleophilic character turn on. And often metal-allyl species are actually cationic, and so probably in my notes today you'll see some drawn cationic and some not when I'm just talking generic metal M, and that's just probably when I'm getting confused, when I'm being fast and forgetting to balance my charge.
Can I ask a question about the delta pluses on the allyl metal?
Yes.
Like up a little bit. Yeah, is it just, do you just know that based on like where the nucleophile is attacking, or is there a way to like explain it otherwise? That it's on the delta plus is on the terminal positions?
Yeah, I think in terms of the empirical evidence for this, there's the reactivity component. It's also evident if you take like a proton or C13 NMR of a metal allyl, you will see that the terminal positions are shifted way downfield compared to the internal position. And there's in the handout that accompanies day 14, you can see some specific examples and kind of walk through that data and unpack it for yourself.
So then, Kiri,
Yes.
does that mean you can predict reactivity based on proton shift?
Ah, great question, Daniel. I'll come back to you then as a volunteer for one of our next questions.
And
no
then,
good deed goes unpunished in this class. Yeah, Camille.
I guess I don't understand what you're showing with the, like, the part below, like, that you highlighted.
Which part below? Sorry.
Like all the metal carbon bonds that you've drawn in the delta pluses and delta minuses. I don't understand what that's showing.
In terms of the metals, the organometallics species ability to serve as an electrophile, this is the general order of reactivity. And the only point I'm trying to make is that the charge distribution that like what under typical circumstances, really only metal-acyl and metal-allyls have sufficiently low-lying LUMOs to be able to be directly attacked by nucleophile. There actually are, we've done this in our lab before, in some cases where metal alkyls can serve as the electrophilic component. Maybe I should like make this, I can do this like this is, these are even more delta minus. Metal alkyls can sometimes actually serve as electrophiles, and that becomes basically not possible when you're in metal-aryl regime, or even less common, put it like that. I'm not going to say not possible. So it's basically just a way to orient everybody in terms of how to think about whether something's electrophilic or nucleophilic.
Sorry,
yeah,
Kiri.
good question, Camille.
I have one more question. Is it generally expected for the nucleophilic attack to be like an outer sphere mechanism as you drill, or?
We'll cover this. It depends on the nature of the incoming nucleophile. That's the short answer. Okay, so we've seen this before, that metal-allyl species are capable of these so-called heptotropic shifts in between the eta-3 form and the eta-1 form. And typically, and again, in terms of their ability to serve as an electrophile, the eta-3 form is more reactive. If you think about this heptotropic shift from eta-3 to eta-1, a coordination site is opened up when you get to eta-1. And so a way to drive that equilibrium is to add more monodentate, strongly sigma-donating ligand. And that can be a trick that's employed, for example, when you want to promote racemization of a stereochemically defined metal-allyl species. And then both of these in principle are capable of reacting with nucleophiles, although reaction at the eta-3 is typically faster. Most of the examples I'll cover in today's class are allyl palladium, which I think is a convenient way to introduce these concepts. There are other metal-allyl species that are also important in catalysis, and I'll talk about what some of the similarities and differences are. Okay, let's go ahead and take a look at problem of the day number 1, which I've reproduced here. And this asks you to consider this cationic molybdenum species. And first thinking about the Davies-Green-Mingos rules, what organic fragment would be attacked by a generic nucleophile Nu-, and then which site in the case that there are multiple inequivalent sites that could be attacked. So let's say, Daniel, you hinted at this phenomenon, so I'll put you on the spot here. First, which of the 2 organic fragments, the pi fragments, would be attacked?
The allyl fragment.
Okay. And now you have 2 potential paths of attack.
I would think it would be the one syn to that nitro.
Syn to the linear NO, and why do you say
Yes.
that?
The nitrogen is more inductively withdrawn.
Okay, that's reasonable, I think. What other electronic effects might be at play here? So I think you're totally right that your intuition that the carbon atom that has more delta plus is going to be the one that is attacked, but which one has the more delta plus maybe is not totally obvious just looking from the structure. So let me direct you to this sort of hint down here, back, and this brings us back to an early concept from class, namely the trans influence. So
Okay,
which
yeah,
of these
then
2
it'd be-
ligands
it'd
has
be
a stronger?
the one trans to the linear nitro ligand, because it has a stronger trans effect.
So what has a stronger trans influence? NO, linear NO, or CO?
I thought linear NO.
Does the class agree here? I have to double check my notes to see if we even had linear NO on the list that we covered, which we might not have. But I think the COs are in general pretty. You unmute yourself, Tanner.
Yeah, they're very close. So in this case, you need to consider like both the sigma donating properties of the NO versus CO and the back bonding. But yeah, Daniel, they can be very close. I think in the Hartwig textbook they put them as like roughly equal.
Okay, so in general, just to draw attention to this rule below, ligands that have stronger trans influence end up providing more delta plus to the allyl carbon opposite, and thereby favoring nucleophilic attack at that position. And I should draw, I guess, a thusly open coordination site. Good questions on that. We'll cover some more clear-cut cases and that don't require you to know all of the intricacies of your trans influence or trans effect series.
What's the geometry of the molybdenum starting material?
I guess this is a piano stool complex. So these CP metal complexes with 3 ligands, their molecular geometry is referred to as piano stool oftentimes. But I guess if you want to bring it all the way back, it will be 6 coordinate, and so it's sort of quasi octahedral or distorted octahedral.
Yeah, these ones are a little different than the molybdenum ones. They have the allyl fragment bound in the 8-3, so it's maybe more similar to being 7 coordinated, such that
That's a fair point. Okay.
Yeah, if it's say rhodium, it would certainly be the distorted octahedral, but this one it's more like 3 on the top, 4 ligands on the bottom, so it's trigonal square pyramidal. If that makes sense.
It's still a piano stool, but piano stool with four legs, I guess.
Yeah.
Okay. Yeah. Thanks, Tanner. That's right. This should be 7 coordinate if you count it. 3, 2, 1 for the CO, 1 for the NO, 3 for the CP, and 2 for the allyl, and I guess many molybdenum 2+ complexes are 7 coordinate. So, okay. So just to read through these rules then and unpack them. So attack of nucleophile occurs preferentially trans ligand with a higher trans effect or influence. You see this in terms of the physical manifestation of this. You'll see this in the X-ray crystal structures by lengthening of the metal carbon bond. You'll see this in NMR spectra by having the carbon and protons that are trans to strong trans influence ligands being downfield, and then this, in terms of reactivity, this means that you're getting more positive charge accumulation at this more weakly bound carbon atom.
I have a quick question.
Yeah.
So if there is a substituent at either one of these termini, can this sort of trans effect promote diastereoselective nucleophilic addition?
Yes. I'll show. Maybe I'll show. I think I have. I'll fast forward ahead and then come back to this point. So what you're asking about Noor is essentially this. Can you use a trans effect to influence site selectivity? And then if you design a ligand, let's say, that has a stereocenter next to the position where you've now encouraged the nucleophile to attack, can you control an anti-selectivity? And so that's the design behind ligands like this Fox ligand. Because the stronger trans effect, it's PN bidentate phosphorus has a stronger, phosphine ligands have stronger trans influence than sp2 nitrogen. So that directs the nucleophile to attack adjacent to nitrogen where the stereochemical information is, if that makes sense.
Yeah, thanks.
Yeah. And then Dan correctly spotted this potential competition between the eta5 CP and the eta3 allyl, and again, these rules suggest that there's typically going to be a preference for open carbogenic fragments. Okay, let's jump into problem of the day number 2 then, which focuses on how to generate metal allyls in the first place. And the most common way is through oxidative addition of an allyl leaving group substrate. And so based on what we've covered before in oxidative addition, we've got a poll queued up. Well, first, I guess, let's first ask someone to just determine what the product of this is, and then we'll load the poll. So we've got these allylic alcohols protected as their corresponding benzoates, reacting with stoichiometric palladium 0. Palladium DBA is a common sort of stabilizing ligand. So what's the product going to be of this reaction, Huiqi?
Hello. So, I think you would form the Metal-allyl species that you I don't know, just the ester group come off and you form the Metal-allyl species.
Okay, and is it going to be at the top or the bottom of the ring?
It should be
Well, let's give a hint here. So the first step is going to be coordination of the metal to the pi system. And is the metal going to coordinate from the top face or the bottom face?
should be the bottom face because left direct hindered.
Okay. It's less sterically hindered, and it turns out that also there's a lower barrier for this oxidative addition to take place via this anti-pathway as well. So, okay, Huiqi got us started here. Oxidative addition. We can draw the benzoate still bound here. And then I guess this is actually probably cationic. So we've got two phosphines present. And Huiqi, what's the abbreviation DBA, just in case anyone hasn't seen this before?
Sorry, I don't know the full name of it.
Okay, you probably know the structure, but maybe not the name. So this is dibenzylidine acetone, just a common neutral ligand, especially for palladium. Typically not involved in catalysis. Okay, and Huiqi, what about the relative rates of these 4 potential substrates?
Did you want to launch the poll for this, Kieran?
Oh yeah, okay, thank you, Van. We almost spoiled it. Huiqi and the rest of the class, what is the order of these that you would expect to react based on what we've already seen in the class in terms of oxidative addition patterns? I think Van set it up in a way to try to trick people for this methyl methoxy. If you're going too fast, you might you might register your vote. Too quickly. Okay, let's end the poll. So I think most people had the right idea. I think some people might have just clicked on the wrong thing, which is that these have this relative rate. And just to orient everybody, this ends up spanning more than 2 orders of magnitude. It's a huge effect from what seems like a minor change. And it's so extreme that in the paramethoxy case, there's actually no reaction. Let me just pull up this, let me jot down this reference. There's actually a lot more to this particular paper than just this set of experiments, but okay, very good. So we have a couple, I see warning signs that my internet is unstable, which is always unwelcome news, but we'll continue to press on. And if there are any issues, we'll do like what we've done before. I'll try to make a recording. So we've seen some key features of this oxidative addition step to generate pi-allyls. One is that it's accelerated by better leaving groups that are more electron-withdrawn. The other feature is that the oxidative addition step itself is typically stereoinvertive. So the first step is coordination of the low valent metal to the alkene opposite to the departing leaving group, and then oxidative addition, which expels that leaving group. But oxidative addition is not the only way to generate metal-allyl species. So let's just quickly brainstorm others, some of which we just saw earlier in this class. So I'll just take this, leave this open to volunteers, and anyone who wants to chime in, please chime in. But don't all chime in at once.
You can add a metal hydride to like an alkyne or a diene.
Well, not alkyne, but I'm totally on board with what you said about diene, Nathan. I think alkyne would give you just the alkenyl palladium. We saw that. So metal hydride, or in general, organopalladium. I think what you were maybe alluding to, Nathan, I'll just fill this one in as well, was the allene addition, which would also be potential palladium 2 hydride. And any other ideas? These are things we haven't covered, but if anyone has thoughts here.
Can you do like an allylic oxidation?
Ah, I love it. Thank you, Nathan. So a very important mode of reactivity where from a simple alkene, you can coordinate palladium 2, which of course we've seen has this pi-Lewis acid activation effect. Coordination of palladium 2 serves to activate the allylic CH bonds, or acidify them, I should say. And then in the presence of an acetate or carboxylate base, now these can be plucked off to generate pi-allyls this way. And this is actually one of the commercial ways by which allylic alcohol is performed. So propylene undergoes this process to generate allyl acetate, and then which then can be hydrolyzed to allylic alcohol or used in that form. And then the last one is just the same general idea of oxidative addition, but with the opposite polarity, where we come in with an organometallic pi-allyl. So think here like an allyl boron, allyl silicon plus palladium in the +2 oxidation state. So you generate the allyl by transmetallation. Okay, and this will bring us to this example here. So you have this interesting looking tethered aryl halide allene compound in the presence of palladium 0 and silver fluoride. Stone, what do you think might happen here?
Oxidative addition into the carbon-iodine bond.
Okay, then what? So you've got an organopalladium species, and now you're tethered here.
Coordination of the, or like, I guess, attack of the enamine.
Attack of the enamine. Okay, where are you forming? What bond are you forming?
So you form the bond between the middle carbon of the allene and palladium.
Ah, okay, beautiful. Man, I typically love using this duplicate feature, but this is one where like none of the, there are geometric changes between every intermediate that I can't use my favorite feature. And then what, so we form this bond between the middle carbon of that allene, which now is here, right, Stone?
So what is palladium between that?
There is palladium between, are you saying like this?
Like you form the 6-membered,
1, 2, 3, 4.
I was gonna say, you
cycle.
form the 6-membered Halder cycle, and then I guess what you've drawn happens afterwards. Or...
Okay, and then what's generated? Or what is this species? I guess maybe I'll draw it since I half drew it already. So now you have a pi-allyl, and then get us home here, Stone. Is there anything in solution that strikes you as being potentially nucleophilic?
I guess you form the primary fluoride.
Ah, beautiful. So Stone's pointing out that we have this silver fluoride in solution, which is an F- source. F- is not typically a great nucleophile, but if you look here, what else is there around? Not much. And so Stone's saying that at the end here, we can get out our primary, I think you said primary allylic fluoride. And how did you think about which position would be preferred here, Stone?
Sterics and thermodynamics.
Okay.
Like you're forming an indole.
Very good. So the product
and
is
also the fluorides, and also the exocyclic positions start with referred.
perfect. Any questions on this? So allylic substitution is in many ways well established. There are still significant challenges, and one historically until maybe 10 years ago was using fluoride as a nucleophile. And my previous PhD supervisor, Veronique Gouvener, in parallel to, and as in collaboration with John Brown in parallel to Abby Doyle, actually tackled this problem. And so this is an example from Abby Doyle's group. But if you look at the worksheet, Abby is not the chemist of the day. The chemist of the day is the first author from this contribution, who's Marie-Gabrielle Braun, a French-American chemist, did her PhD at the École Polytechnique with Samir Zard. We had Samir for a talk, but maybe too long ago for most of this audience. And then she did her postdoc with Abby Doyle and has established a really successful career at Genentech. Our first chemist of the day, though perhaps not our last, from an industrial institutional affiliation. And so not only during her postdoc, not only did Marie Gabrielle develop this nice chemistry, but developed a way to make allylic fluorides directly from alkenes, coming back to this this type of reactivity paradigm above, and I think inspired at least in some part by work from Christina White, who's shown a range of different nucleophiles that can participate in those sorts of processes. Okay, any questions on that?
Hi, Gary.
Hi, Joan.
Yeah, I have a question. Two questions, actually.
Sure.
Yep, so for these type of reactions, I just wonder what is the solvent for these reactions? And the second one is, suppose the F minus is the nucleophilic source. So what about using some other fluoride source, for example, cesium fluoride or potassium fluoride? Does the reaction work well compared to silver fluoride?
Yeah, these are good questions, June. I have this reference open. I think you'll also receive it if you haven't already. But I think the key is that they use these these low dielectric constant solvents. I think they have different methods in the paper, but there's DCM and toluene. The nature of the fluoride source, it's actually, there's a lot to this question, which maybe is why you're asking it, is critical, because allylic fluorides themselves are competent electrophiles for oxidative addition of palladium-0. So you need to have some way to drive this reaction. And in the Doyle chemistry, they often drive it by using silver fluoride, which ultimately makes a silver halide salt as a driving force and takes the iodide in this case, but they've also used allylic chlorides out of solution. In the case of the Gouvener-Brown chemistry, it's critically reliant on this very special anhydrous T-bath, tetrakis T-butanol T-bath. So this is a critical rule. I think probably both groups have screened every fluoride source on the planet, and it's normally specifically dependent on the one that's reported.
So can I just interrupt with the part about silver?
Sure.
So is silver fluoride soluble and silver iodide isn't? Or is it just more like halophilic for iodides? Like what's actually pushing that, since they're both halogens?
I think this goes back to hard, soft, acid-base theory, that the bigger and less electrophilic halogens, chloride, bromide, and iodide, form stronger interactions, stronger bonding interactions with silver, which itself is a soft metal, silver one.
Okay, yeah, that makes sense. Thank you.
Okay, so now we'll jump into the catalytic turnover part of this, which we already got a teaser about in this example. And we'll go through some of the questions that have already arisen. So in terms of synthesis and synthetic planning, as you will all appreciate at this point, allylic substitutions are powerful because they allow these SN2 or SN2 prime type processes which in the absence of a catalyst are often not very clean and not very selective. And so it allows you to do this transformation that's familiar in organic chemistry, but in a way that has higher selectivity than you can from just the old fire and brimstone approaches. The nucleophiles that are engaged, we just saw a counterexample of this with fluoride, but in general, the nucleophiles that are most commonly engaged are soft nucleophiles, which is defined as having a pKa less than 25. So if it's a carbon nucleophile, having an enolizable proton, for example, if it's a nitrogen nucleophile, having that be activated by a carbonyl or sulfonyl group. And then the overall stereochemical outcome, we saw already that oxidative addition is stereoinvertive. With soft nucleophiles, that nucleophilic attack is also invertive, so that the product of double inversion is overall retention. With hard nucleophiles, we'll cover this briefly, things like Grignard reagents or things with non-enolizable carbon nucleophiles with non-enolizable protons like simple esters, monoesters, those typically need to first pre-associate to the metal before being delivered to the allyl fragment. And that nucleophilic attack step ends up being stereo-retentive, making the overall process inverted. So here's now these steps all put together. We start with oxidative addition. We start with coordination. And then oxidative addition. Now the oxidation state of the metal, which was just N, is raised to N+2. These, as I said, are often drawn as cationic. Now we have a nucleophile attack. So we all get used to seeing this. I'll draw this out. So this can attack one of the two carbon atoms, and then in either case you have electrons from the organic fragment formally being transferred to the metal, two possible regiochemical outcomes, and then a dissociation step. So just like we did with the nucleopalladation chemistry, I think it's fun and instructive to take a look at some of the early history of this. I'll draw your attention to two key reports, one from the Tsuji laboratory and one from the Trost laboratory. Obviously, if you're up on your name reactions, it will come as no surprise that these are important examples to highlight in the context of allylic substitution. Tsuji had this interesting report in 1965, and if you're following carefully on the dates, this came shortly after his report where he took palladium COD complexes and reacted them with deprotonated malonate nucleophiles, where he's trying to extend Walker type reactivity to carbon nucleophiles. Now he's asking what other organic fragments could potentially be electrophilic in this type of addition, and he takes palladium allyl chloride dimer, adds deprotonated diethyl malonate, and indeed sees the product in a stoichiometric sense of allylic substitution. And Tsuji and some of his colleagues were actually able to develop this reaction, which in this instance is stoichiometric, into a catalytic version. But I think the full synthetic value of this transformation wasn't fully appreciated until the contribution from the Trost lab in the early 70s. And one of their key findings, it really echoes like some of Wilkinson's work, was the use of triphenylphosphine as a ligand to give drastically accelerated reaction rates and cleaner reactions. And his lab carried out this study in the context of a synthesis campaign. And one of the interesting points to note here is that this palladium 2Al pre-catalyst was actually an example of one where it's generated from the CH activation pathway, not from the classical oxidative addition pathway. I guess just a fun factor. Maybe I'm the only one who finds that a fun factoid, but I'm teaching the class, so you have to pretend that it's fun. And then very early on, Barry the Trost group as synthetic chemists appreciated that this transformation would have increasing value if it could be increased value if it could be rendered enantioselective. And so starting all the way in the early 70s, and again, this is now echoing the timeline of what we saw from the likes in the asymmetric hydrogenation field from the likes of Knowles, Kagan, etc. The original chiral ligand that they found some success with, and this is all nicely documented in this accounts of chemical research from Trost, was a chiral at P ligand. Shown here. With one cyclohexyl group, methyl group, and then this ortho-substituted aryl group. And the ultimate culmination of the better part of 20 years of dedicated research was this ligand family, which we call now Trost ligands. And this is a hard nut to crack in terms of stereochemical induction, because if you think about where the ligand sits in relation to the incoming nucleophile, so let me just back up here to make this comment. If you think about where the ligands are here, they're way on the opposite face to where the incoming nucleophile is. So it's a real challenge in ligand design. You either need to have some significant conformational gearing, or you need to have ligands that really extend back in space towards where the allyl fragment would be oriented. And on one of part of your handout chronicles more examples of enantioselective protocols, how enantioselectivity can manifest itself in this chemistry. And so I direct you to that for more information. In terms of relative reactivity of electrophiles, we already saw this case with substituted benzoates, but more generally, there's a clear effect in terms of the activating group on oxygen, on how quickly these can react, where allyl carbonates are typically the best, followed by these allyl phosphonates, and then allyl acetates or benzoates here. And the allyl carbonate has a special property that I think makes it often, when you can use it, the electrophile of choice. I don't know if anybody sees this. So why would allyl carbonate be especially reactive and useful in this context? Any takers? I think we just talked about this in group meeting not too long ago. Is Omar here today? No? Oh, he has an excused absence. Okay, that's too bad. He asked this question. So if you think about this oxidative addition, then loss of CO2 actually generates methoxide as anion, which can serve as the base for deprotonating the incoming nucleophile. So it's a nice way to package all of what you need in one functional group. Okay, and now let's come to this question, which echoes some of what Dan was asking, some of what Noor was asking. So we've talked about the effect of ligands and how the trans influence can bias the site that is preferred for nucleophilic attack. But of course, the nature of the organic fragment itself and its substituents can bias the site of attack in significant ways. And so this example here, and this information is available as well on your handout, tries to address this question in a systematic way by varying electronics of the organic fragment. So if you had, so shown here is this Allylic substitution reaction, generic nucleophile. If you had to guess, Kelly, the left or the right, which would you predict is preferred?
Probably the right.
Why do you say the right?
Because the nitro containing ring is the more electron poor.
I think that is a totally reasonable way to think about things and is the opposite of what is empirically observed. Did I set you up, Kelly? Sorry if I set you up. If you want to watch me mumble my way through explanation of this, then you can go to last year's video, because even though I had it in my notes, I thought my notes were wrong, and yeah, anyway. And so the way to think about this, at least in terms of a mnemonic, is think about the pi-allyl in terms of how it's reacting as a allyl cation. And consider the ground state electronic structure. So in this case, sorry, you have two aryl groups. And the aryl group where the cation, or the resonance form where the cation is adjacent to the electron rich group, resonance electron donating group, you expect to be more stable, and thus sort of the predominant form in solution, if you want to think of it that way. Another way to think about this is think about how the dipole that is generated during the transition state, where you're getting electrons flowing from the organic fragment to the metal, and how that would align with the preferred dipole of the aryl groups. So we've already talked about how ligands can then influence which site is preferred. Those with greater trans influence, direct nucleophilic attack to the site trans to them, and then how that can be integrated as a design feature, particularly in things like PN ligands, where you have two different heteroatoms coordinating to the metal. Okay, let's discuss now this dichotomy between hard versus soft nucleophiles. So as I said, when I refer to hard nucleophiles, I'm talking about things like Grignard reagents, where the key point is that transmetallation is expected to be fast compared to nucleophilic attack. So here, from an enantiomerically enriched allyl palladium, we can see the divergence in stereochemical outcome, where the hard nucleophile will react via transmetallation reductive elimination to give retention in this step. Although you do get some stereoablation, and we'll talk about that, where that's coming from. Whereas the soft nucleophile, deprotonated diethylmalonate, is reacting with inversion here by an outer sphere process. And then the intermediates that are thus involved the aryl coordinated inner sphere, beta 1, versus I guess this is not really an intermediate, this is sort of a quasi transition state, but now this attacking either of these two sites, backside attack, reminiscent of an SN2. So this illustrates this point that we've been touching on, that inversion takes place for soft nucleophiles in this nucleophilic attack step, retention for hard nucleophiles. We talked about the electronic influence of site selectivity. There's also a steric influence, which is that at least in the palladium chemistry, and we'll talk about how this is different with different metals. At least with palladium, typically product CC or C heteroatom bond formation is taking place at the less substituted allyl terminus, and site selectivity here can be dictated in addition to the nature of the substrate by the ligands on the metal.
Gary, I have a question here. So when you say hard and soft and you have the two sort of extreme examples here, I'm wondering, so if you had, I don't know if you would consider like a hard deprotonation of an amine, would that go through an inner sphere like that? Or would it do more of like the malonate or would that still be considered a soft nucleophile? I guess not. It'd probably be a hard nucleophile.
What type
Is
of
that,
amine are you
is that type
talking
of
about?
chemistry known? Like a deprotonated amine. Like if you had that as a nucleophile, is that chemistry known? Do you know if that proceeds via the inner sphere or outer sphere?
Yeah, I think there's, like with the carbon series, there's a pKa dependence. So I think NH containing nucleophiles that are more acidic can react via the soft pathway. Do I have that right, Van and Tanner?
Yeah, things like phthalides can be quite different than, yeah, something like a aniline.
So we've been focusing mostly in this regime in the preceding discussion with palladium. Nickel is kind of its own, has some of its own rules, but I also want to draw your attention to that a complementary body of work. I think notably with iridium, where reactions are with similar substrates, similar chemical inputs can instead be branched selected. And so this for synthetic blending is nice because based on your choice of metal and ligand set, you can grant access to either possibility. And then there's been a beautiful body of work with copper as a metal as well. And it's kind of its own self-contained field of work. So much so that Hartwig actually covers it as a separate, as a completely separate section. And with copper, some of the, and here I'll highlight the works of the likes of Alexakis and Hoveda, who really made this a reliable synthetic method that can even be performed enantiote selectively. So what differentiates copper from these other metals mentioned is that it's typically works best with hard nucleophiles, your organo zincs, your Grignards, your organolithiums, typically is branch selective, and then overall invertive, as we've seen for sort of the hard nucleophile theme. And the mechanism here with copper, I think is as I said, a little bit different. And so I just draw your, in the interest of time, we won't cover that, but I just draw your attention to that chapter of the textbook for those who are interested. So when we talk about the potential stereochemical outcomes of allylic substitution, it's important to think about processes by which stereochemistry can be created or lost from the metal-allyl. So we talked about how ligand association and oxidative addition is typically cleanly invertive. But that doesn't necessarily mean that the pi-allyl is going to be indefinitely stereochemically defined. So there are processes by which pi-allyls can racemize. And the one that probably immediately comes to everybody's mind is that by toggling or undergoing a haptotropic shift to, I guess I'll draw these all as cationic just to be consistent, by undergoing a haptotropic shift from eta 3 to eta 1, that doesn't look like an eta, that looks like the stereochemical information that contained in the eta 3 form is lost. And then when the eta 3 form is reformed, now either an enantiomer could potentially be formed. And so the overall stereochemical outcomes of an allylic substitution not only depend on whether the reaction is stereotensive or invertive, overall stereotensive or overall stereoinvertive, but also the relative rates of the eta-3 to eta-1 back to eta-3 isomerization. When these are tuned appropriately, you and everything is on your side, you can even have situations where you go in with non-stereo defined racemic starting material and engage in a dynamic kinetic asymmetric transformation to get out a single enantiomer of the product. Now the internal case is a little bit different because when you undergo the haptotropic shift from eta-3 to eta-1, now you still maintain point chirality at your carbon metal bond. And so this can go back and forth, but you don't lose any stereochemical information here. Provided that R1 and R2 are different. But there is still a way by which stereochemistry can be inverted. And I'll just invite if anybody has an idea to shout it out, and then we'll wrap things up.
Could it make an allene and then hydride insertion?
Oh, that's interesting. Yeah, that's an interesting proposal. I think in principle it would be possible, but I would imagine that step would be thermodynamically uphill. So you can invert here by another molecule of your metal catalyst, finding the pi-allyl and essentially bumping into it and just knocking the other metal off. And this is I kind of like, I don't know, vaguely analogous to how stereochemical information can be lost in like halonium ions, where they can be formed in anti-pure fashion. Scott Denmark has shown that then another molecule of alkene can bump into the halonium and ablate stereochemistry through that pathway. So we're almost to the end of the notes. I mentioned previously that there's a handout that has much more discussion about enantioselective control of these reactions. There are many things you can do here. You can use a prochiral nucleophile and set stereochemical information on the nucleophile. You can use prochiral substrate and establish stereochemistry there. And so this is summarized in a handout in this nice review from Trost. Now it's a little bit dated, but I think still gives a very nice overview.
Hey, Kiri.
Yes.
For the internal case, for the stereo inversion of the metal-allyl complex, you show that as being like one in one direction. Is that not reversible, or can it be driven forward and to one side based on like the R groups or the ligand identity?
You're talking about this case here?
Yes.
Sorry, what's your question? Like if it's reversible,
yeah,
how to bias it one way or the other? Is that what you're asking?
No, I was just making sure it was reversible because it was shown as one direction, and I was wondering if there was, if you were saying that there was any kind of driving force.
Sorry, are you talking about this case here, Daniel?
Yeah. Yes.
Oh, but I'm drawing this as reversible.
Okay.
Yeah.
That's what I was making sure.
Okay.
Thank you.
Yeah. Okay, so we'll wrap things up here and be respectful of everyone's time, a few minutes over. And then we'll start things off by taking on problems of the day 3 and 4 to kickstart our next lecture. Thanks everybody and have a great weekend.